So let us now work through a couple of practice problems to make sure that these concepts are well understood. So in the first question, we have that there is a risk-averse individual who can invest in one of the three types of assets that are available: government bonds, corporate debt, and equities. So the individual is free to invest different amounts of his wealth across these three different assets. So we also have some information about these three assets. So the government bond is basically a risk-free asset, and the rate of return on the government bond is given by 2%. The corporate debt has a expected value of 6% and a standard deviation of 5%. And the equities has an expected value of 12% and a standard deviation of 20%. So we can see from here that the corporate debt and equities are both risky assets because they have a positive standard deviation. And we can see that basically equity has a higher expected return, but also has a higher standard deviation compared to the corporate debt. We are also told that the correlation coefficient between the two risky assets, so corporate debt and equity, is given by 0.25. Okay. So on the basis of this, we'll answer a set of questions. And I encourage you to, at each point when you see a question, just to pause the video and try and attempt it yourself before you look at the solution. So what's the first question? So it's asking what's the smallest possible variance of a portfolio which consists only of debt and equities? And what are the portfolio weights for these two assets? So basically, we are looking at creating a portfolio which consists only of the risky assets, corporate debt and equities. And the question is, what's the smallest possible variance that we can do that, right? So let's look at how to go about solving it. So suppose that WE is the weight on the equities, and so therefore the weight on the debt part is going to be 1 minus WE, and sigma P is the standard deviation of the portfolio. So what we want to do is we want to choose the weight WE to minimize this standard deviation, right? So what's the variance? So variance is given by sigma square P, and that is, as usual, applying the formula, we get that it will be equal to the weight on the debt part square. So that's equal to 1 minus WE square, sigma D square. So this is the variance of the debt plus weight on the equity squared multiplied by the variance on the equity plus 2 times the weight on the debt, 1 minus WE, times the weight on the equity times the covariance of the debt and the equity, right? Now, we want to rewrite this a bit more cleanly. And the way to do it is that we actually notice that this is a quadratic equation in the uh, WE term, right? So we just arrange it so that we collect the coefficients of the quadratic equations carefully. So we have that weight of the equity square. If you look at where are the square coefficients coming from, so you'll have one coefficient from this part, which will be this sigma square D. Then you'll have another coefficient from here, which is sigma square E, plus are going to have minus 2 times sigma DE. Now, sigma DE, actually, we have the information in terms of the correlation. So we can rewrite sigma DE as the correlation multiplied by the product of the standard deviations. And that is what we have here, right? Now, what's the constant term in this quadratic equation? It's actually just sigma squared D. This is the place where it's coming in. That's the only constant term that we have. And you also have a plus WE times, again, some coefficient that we have to figure out. So you're going to get one expression from here, minus 2WE sigma D square. So we have taken the WE out. So you have got minus 2 times sigma squared D. And another term you'll get from here. So that will be plus 2 sigma DE. And again, writing sigma DE as rho DE into sigma D into sigma E, we end up getting this expression, right? So the whole point is to write this as a function of W square E and the parameters that we have. Now, at this point, we can actually put in the parameter values. And it turns out that here the parameter values are chosen so that the algebra becomes a bit easier. So if you do plug in all the parameter values, you will find that what you end up getting is that sigma square P is 0.0375 times W square E plus 0.025, right? The reason is basically based on the parameter values, this one actually ends up being equal to 0 here, right? Now that simplifies our problem a lot because now we don't have to actually do any complicated optimization exercise here, right? We can just observe that the lowest value of the uh, sigma square p that we are going to get is going to happen when WE is equal to 0. And therefore, the smallest possible variance that we are going to get is just equal to 0.0025, right? So that's the one that we have. And this will be a portfolio which has zero weight on equity, and so therefore will consist entirely of debt, right? So you can also see from here, this is just 0.5 square, 0.05 square. Okay, so that was the first question. Now let's look at the second question. So it's asking find the expected return, standard deviation, and Sharpe ratio of a portfolio composed of an equally weighted mixture of equities and corporate debt. So an equally weighted mixture of equities and corporate debt tells us that the weight on the equity is half, and the weight on the debt part is also 1 minus half equal to half. So we can actually then plug in all the expressions. So WE is equal to half, and expected return on the portfolio is the weighted average of the return on the debt and the equity, where we are told that the weights are equal to half. So therefore, this becomes 0.5 multiplied by 0.06, which is the return on the debt, plus 0.12, which is the expected return on the equity. And so therefore, this is equal to 0.09 on 9%. So that's the first part. How do we go about calculating the standard deviation? Well, this is the expression for the standard deviation that we have. And we have already actually figured out in the previous part that this can be simplified in this case to write it as 0.0375 W square E plus 0.0025. And so we just have to plug in the value of W equal to half here. And if we do that, we end up getting the variance equal to 0.011875. And the standard deviation is nothing but the square root of this term. So that's approximately equal to 0.109. So around 10.9%. The third part asks about what is the Sharpe ratio. So we have got the expected return. We have got the standard deviation. So the only other ingredient that we need is the risk-free rate, but that is also given as a parameter to us, right? That's the 2%. And so we can put all of this together so that the Sharpe ratio of this portfolio is 0.09, which is the term that we had here, minus 0.02, the risk-free rate. And in the denominator, we have the standard deviation. So if we do the approximation, this turns out to be approximately 0.6424. Okay. All right. Now, this was for this particular portfolio. The next question asks to actually figure out the expected return standard deviation and Sharpe ratio of the optimal risky portfolio. And we are also asked to actually figure out what are the weights for these two assets, right? So remember, the optimal risky portfolio is the one which is basically the consisting of only these two risky assets, the corporate debt and the equity. And it is basically the tangency portfolio, right? So this is the portfolio for which the Sharpe ratio is actually maximized. And so therefore, what we want to do is we want to write the Sharpe ratio as a function of the weight of the equity, let us say. And then we want to choose the weight of equity so as to maximize this. So we proceed as follows. So the Sharpe ratio first step is the definition. So if any portfolio P that you have chosen, the Sharpe ratio is expectation of the rate of return for this portfolio minus the risk-free rate divided by the standard deviation. So we can rewrite the expected return of the portfolio in our standard way. And sigma P, we have actually already derived an expression for, right? Which is this expression that we had here. And so therefore you end up getting the Sharpe ratio as a function of just WE. Now, at this point, you have to choose WE to maximize this Sharpe ratio. So you can see that WE appears both in the numerator and the denominator. So you have to use basically product rule here, right? And if you do that and then simplify here, actually it looks a bit more complicated than it is. So if you do the simplification, so what you end up getting is that WE is equal to 0.1, right? So that means that the portfolio weights for these two assets are such that you are going to put 10% in the equity and 90% in the debt for the optimal risky portfolio. So that actually answers first our last question. And Then once we have the portfolio weights, we can actually figure out what's the expected return, standard deviation, and the Sharpe ratio, right? So let's look at that. So expected return is again the weighted average. We now know that for this optimal risky portfolio, the weight of the debt will be 90% and the weight of the equity is 10%. So therefore, the expectation of RP is going to be zero point 0.9 times 6% plus 0.1 times 12%. And that is that is actually equal to 6.6%, right? So that's the expected return. How do we calculate the standard deviation? So again, we have this expression that you see here, and we can actually now put in all the terms that we have. So sigma squared per, put in WE is equal to 0.1. So this 1 minus WE becomes 0.9. You have got the sigma squared D, sigma squared E, and sigma DE as the different parameter values. And so therefore we can put all of this together, and we end up getting that sigma squared P is given by 0.002875. And so therefore the standard deviation is the square root of this, and that's approximately equal to 0.0536. Okay, so how do we calculate the Sharpe ratio? So again, it's equal to expectation of RP minus RF by sigma P. So we have calculated expectation of RP. We have calculated the sigma p, and we know that the risk-free rate is 0.02. So again, if you plug in all these things, you see that this is equal to approximately 0.8579. So we know that this is actually much higher compared to the previous Sharpe ratio that you found. And that kind of like at least makes sense that, it should at least be higher, right? Even if it's not much higher, because this is the maximum possible Sharpe ratio that you're looking for. Okay, so let's look at our next question. So this says that suppose an investor constructs a portfolio with expected return 10% by combining only debt and equities. What is the standard deviation of this portfolio? What are the portfolio weights for these two assets? So if you notice, like we are asking different variations of questions that one can think of here. So this is about somebody who wants to target this expected return and is just using these risky assets, right? So the question is, okay, if you want to do that, what is the weight that you want to do, and what is the standard deviation that will accompany this as a result of the weights you choose, right? So first, let us find out the weights. And how do we find out the weights? Remember, the target is that 10% is the requirement. And we know that for a portfolio which consists of only these two assets, the expected return is just the weighted average of these returns, right? So suppose WE is the weight that you put on the equity. So then you get WE into 0.12 plus 1 minus WE into 0.106 is actually equal to the 10% that you want here. So there's a typo here. This should be 10%. So if you do 10%, so that means 0.1. If you now do the calculation, you end up getting that WE is equal to 2 by 3. Okay, so that answers this question, that what are the portfolio weights for these two assets. So that is going to have a weight of 2 by 3 on equity and therefore 1 by 3 on debt. We can actually now use this to back up what will be the variance of this portfolio. So again, we use the expression that we had previously. We have now the weights, we have the parameter values. So if we put them all together, we end up getting that the variance is going to be 0.0192, and therefore the standard deviation is approximately 0.1384. All right. Now, suppose that the investor wants to use not just debt and equity, but also bonds, debt, and equity to actually construct this portfolio with an expected return of 10%. And the investor actually wants to combine this optimally in the sense that it wants to have the smallest possible standard deviation corresponding to this 10%. So the question is, what is the standard deviation of this portfolio? And again, what are the weights of the three assets now, right? Rather than the two assets. So again, let us start with what the target is. So remember, the idea is that the three weights should be such that the expected return, which is the weighted average of the expected returns of the underlying assets, must add up to 0.1, right? So therefore, we have got WFRF plus WD expectation of RD plus WE expectation of RE is equal to 0.1. Now, you can actually rewrite this WF as 1 minus WD minus WE, because the three weights must add up to 1. And if you do that and simplify, you end up getting this expression here, right? That's the first step. Now, what's the next step? Well, we know that since this is being created optimally, therefore the ratio of WD and WE has to be the same as the one that we had in the optimal risky portfolio, right? So therefore we know that WD by WE has to be equal to 9, right? So what that means is that we can replace this WD here by 9 times WE, and so we end up getting this expression here, and we are also putting in all the parameter values of the different expected returns and the risk-free rate that we have. And now if you do the simplification, this is just a linear equation in WE, right? And you will end up getting that WE is equal to 4 by 23. Now, once you have WE is equal to 4 by 23, you can also find out what WD is, which is 9 times that. So that's 36 by 23. And finally, all the three weights must add up to 1. So from there, you get that this is 40 by 23. And so therefore, this must be the weight on the risky asset must be 17 by minus 17 by 23, right? So that's the answer to, again, what are the portfolio weights? How do we calculate the standard deviation? Well, uh, actually, this is just the weight that you're putting on the optimal risky portfolio, right? Times the standard deviation of the optimal risky portfolio. So remember that we had calculated what's the standard deviation of the optimal uh, risky portfolio here. And we had found that this was equal to 0.0536, right? And so therefore, what's the standard deviation here? So that's equal to 40 by 23 times this, right? Now, why were we able to simplify this expression so much? Because remember, this is basically now at this point a portfolio which consists of this uh, risk-free asset, right? And you have got one risky asset, which is this optimal risky portfolio, right? And you're putting a weight of 40 by 23. So this is basically just recalling the result where you have got one risky asset, one risk-free asset. The standard deviation is the weight on the risky asset times the standard deviation of the risky asset, right? So that's basically what we are doing here. Okay, so final question in this line. So what's the optimal combination of bonds, debt, and equities for an investor whose preferences are given by U equal to expectation of R minus 3 sigma square? Okay, so here we need to basically figure out two things. One is that what is the capital allocation line slope, and what is the this indifference curve's slope going to be, and then equate the two, right? This is the our usual optimality condition. So now we know that the investor is going to choose a cal so that the slope is given by the highest possible Sharpe ratio, which we have already calculated to be 0.8579. And so therefore the cal will have an equation which is of the form expectation of R is equal to the risk-free rate 0.02 plus 0.8579 times sigma. In case you don't recall this, I encourage you to go back and see the discussion of the risk-free asset and one risky asset that we have discussed. So it's coming from there. Okay. At this point, this is the equation of the line, and we need to know the slope of the line. So that is pretty clear. That's equal to actually 0.8579 because this is a straight line. We need to know also the slope of the indifference curve at a particular point. So remember that we draw these diagrams with expectation of R on the y-axis and sigma on the x-axis. So therefore, in order to find out the slope, we will rewrite first this utility function as expectation of R is equal to U plus 3 sigma square, where for an indifference particular curve, U is a constant, right? So if we take the derivative of expectation of R with respect to sigma, which is what we have on the x-axis, right? We end up that this is equal to 6 sigma, right? So at the optimal point, we must have 6 sigma is equal to 0.8579. So 6 sigma being the slope of the indifference curve, 0.8579 being the slope of the CAL. And so therefore from here, we end up getting that sigma is equal to 0.143. Now, how does that help us answer the question? Remember, our question is to find out what's the optimal combination of bonds, debt, and equity. So once we have figured out what sigma is, what we can do is we can figure out what's the expectation of R, right? How do we do that? Well, we have the CAL. So from there, we end up getting that expectation of R is 0.1427. And based on this, now we can figure out what's the weight on the risk-free asset, right? How do we do that? So uh, this is the expected return of the portfolio, and this comprises of the risk-free asset plus the optimal uh, risky portfolio, right? So there's a weight of WF on the risk-free asset, and therefore a weight of 1 minus WF on the optimal risky portfolio. Now, if you plug in the value of RF and this expectation of R over P, so this we had calculated before, remember, um, here this is the expected return of the optimal risky portfolio. So if we plug in these expressions, we end up getting that WF is equal to minus 1.6674, right? So what that means is that the weight on the optimal risky portfolio is 1 minus this term that you see here, and so therefore it's equal to 2.6674. And in that risky portfolio, remember that equity has a 10% share. So therefore, the weight of equity is going to be 10% of this, so 0.2667. And the weight on the debt is 90% of this term that you see here. So therefore, that's approximately 2.4007, right? So this is the final answer, that this is how you can actually find out the optimal combination of the bond, debt, and equity for this investor. Okay, let's look at one more question. So suppose that there are two risky assets available to Gandalf for investment, who can invest either in Gondor or Mordor. So these are basically, think of these as two different risky assets. So the expected returns and covariances for these two assets are that expected return on Gondor is 8%, expected return on Mordor is 6%. The standard deviation of the returns for Gondor and Mordor are the same, that's equal to 28%. And these two assets are uncorrelated. So therefore, the covariance is 0. And there is also a risk-free asset present in this economy with a return of 0%. So first question is calculate the risk premium and Sharpe ratios for the two assets. So here you just have to remember what's the definition of risk premium and Sharpe ratios. So the definition of risk premium for an asset is it's the expected return of that asset minus the risk-free rate. So here the risk-free rate is 0%. So therefore, the expected return of the asset and the risk premium are the same. So risk premium for Gondor is 8% and risk premium for Mordor is 6%. And what's the Sharpe ratio? Well, the Sharpe ratio is the risk premium divided by the standard deviation. So we have calculated the risk premiums. We therefore can easily calculate the Sharpe ratio since we are given the standard deviations. So we end up getting that the Sharpe ratio for Condor is 8 by 28 or 2 by 7. And the Sharpe ratio of Mordor is 6 by 28 or 3 by 14. Okay. Now, Gondor somehow figures out without doing any calculation that the risky portfolio with the highest Sharpe ratio has a weight of 4 by 7 on Gondor and 3 by 7 on Mordor. Okay, so remember, these are the two risky assets. Gandalf figures out that these are the optimal weights in the risky portfolio, right? Based on this, we are asked to calculate the standard deviation, the risk premium, and Sharpe ratio for this portfolio. So let's think about it. First, the standard deviation. So this is going to be equal to this expression that you see here. So let's understand where we are getting these things from. 4 by 7 is the weight on the Gondor, right? 28% is the standard deviation. So 28% square is the variance, plus 3 by 7 is the weight on Mordor. And again, 28% is the standard deviation of Mordor, right? So we can take out this 28% square outside. So that just becomes 28%. And then this expression that you see here, that's going to be just 4 by 7 square plus 3 by 7 square. So that's 16 by 49 plus 9 by 49. So 25 by 49. So that's equal to 5 by 7, right? So if you take the square root. And so therefore, this is equal to 20% or 0.2, right? So that's the first expression. Okay. How about calculating the risk premium? So risk premium is the expectation of the rate of return of this portfolio minus the risk-free rate. Risk-free rate is 0%. So we just need to calculate the expectation of the rate of return. So again, we know the weights 4 by 7 and 3 by 7. And so therefore, this is 8% and 6%, which again, this information is given to us. So if we do the calculation, that turns out to be 50 by 7%. Okay. What's the Sharpe ratio? So that's the risk premium divided by the standard deviation. So we get 50 by 7 divided by 20. And if you do the simplification, this turns out to be 5 by 14. So this is the basically the information that we have for the optimal risky portfolio. Okay, now let's think about the choice problem. So suppose that Gandalf is a mean variance optimizer with our usual utility function. And suppose the value of A for Gandalf is 25 by 14. The question is, what's the percentage of the wealth that Gandalf should invest in the risk-free asset and the two risky assets, Gondor and Mordor? So here again, the key is to take advantage of the fact that first you want to allocate between the optimal risky portfolio and the risk-free asset. And once you have done the allocation, then within the optimal risky portfolio, you want to actually arrange it in this weight, right? So we actually, because this is a straightforward problem in the sense that we have a mean variance optimizer, and we know the risk-free assets return, and we know the information about the risky asset, we can actually go back and use a formula that we had seen before. Again, in case you forget about it, you can rederive it, but these are some formulas that come up often. So I think if you practice enough, you'll actually get these things by memorization, just not by artificially memorizing, just because this comes a lot of times. But in case you forget, you can always rederive these things. Okay. So what's the weight on the optimal risky portfolio that Gandalf will put? So remember that is equal to expectation of RP minus RF by A sigma square P. So we had seen this expression before when we had studied the optimal choice between one risky asset and one risk-free asset. Now, if you notice this expectation of RP minus RF by sigma P, okay, just one sigma P, not sigma P square. So that is nothing but the Sharpe ratio of the optimal portfolio, right? Which we have calculated to be 5 by 14, right? What else are the terms that are remaining? So you have got a in the denominator. So that we know is 25 by 14 for Gandalf. And you have also got another sigma p, and we know that sigma p is actually 20%. So that's actually 1 by 5, right? Now, if you cancel out the terms, so the 14 cancels out, and the 5 and 25, 5 remains, and 5 and 5 cancels out. So you end up getting 1, right? So what this says is that Gandalf is not going to actually keep any of his wealth in the safe asset, but is going to put it all on the optimal risky portfolio. And therefore, we also know now the division, because we know that the optimal risky portfolio has a weight of 4 by 7 on Gondor and 3 by 7 on Mordor. So therefore, we know from there that the percentage that Gondor is going to put on Gandalf is going to put on Gondor is 4 by 7, and the percentage that is going to put on Mordor is 3 by 7. Okay, so now Gandalf has optimized his kind of like utility function and so on. And one day he runs into Boromir, who has all of his wealth invested in Gondor, right? So once Gandalf hears this, he doesn't even need to ask what's Boromir's risk aversion parameter, right? He knows that Boromir is a mean variance optimizer, but he doesn't know what the risk aversion parameter is. But Gandalf says to Boromir that, well, you are just investing inefficiently, right? And why are you investing inefficiently? In the sense that it is possible to actually increase the expected return on Boromir's portfolio without affecting the variance, right? So this is like, you get a higher expected return for free, right? So the question that we want to answer is, what's the highest expected return that Boromir can get, keeping the variance same as his current portfolio? Okay, now why do we know that? Why did Gandalf immediately know that Boromir was doing something incorrect? Because we already know that since Boromir is holding on to a risky asset, what he should have been doing is he should have been holding on to Gondor and Mordor assets in the ratio 4:3, right? Um, so that's one thing that already told us that he is doing wrong. But the question asks us to go a bit beyond, and also to actually calculate what should be the expected return that he can get optimally, right? Okay, so what do we need to do? So essentially, we need to just figure out the point on the capital allocation line which connects the risk-free rate and the optimal risky portfolio. On that line, what is the point corresponding to the same variance that Boromir is getting now. So that will give us the answer, right? Okay. So what is the variance that Boromir is getting now? Because Boromir has only holding on to the Gondor asset, so therefore the his variance of his portfolio is just the same as the variance of Gondor. So that's 0.28 square. And what would have been the case if he had gone on an alternative portfolio, which was on this capital allocation line? So that depends on the weight that he's putting on this optimal risky portfolio. But suppose the weight is W. So then we have got that W square is equal to sigma square P times 0.28 square. Okay. Now, we know the value of sigma square P, right? So remember, this is 0.2. So therefore, sigma square P is zero point 0.2 square. And so therefore, from there, we know that W is equal to 0.28 by 0.2 or 7 by 5. So therefore, W should be 1.4 in order for him to have the same variance as before, but being on the capital allocation line. Okay. So once we have got this weight, we can actually figure out what's the highest expected return, right? Because you have got a risk-free asset which has a weight of 1 minus this, but that is getting a return of 0%, so that doesn't matter. So all the return is going to come in from this optimal risky portfolio. So therefore, that's equal to the weight 1.4 times this 50 by 7%. And again, if you do the simplification, this turns out to be 10%. So we can see that as expected, Gandalf was right. So Boromir was, remember, earning a rate of 8%. How do we know this? Because this is the rate of return of the Gondor asset, right? Which was the only thing that Boromir was holding. If he, in fact, changes his asset so that he's actually investing optimally in the ratio 4:3 on Gondor and Mordor, so he can actually increase his expected return to 10% from the current 8%, with the variance still remaining the same, right? So that's the answer to this question. Okay, so these are some references that you can refer to. One is this classic textbook called Investments by Bodie, Kane, and Marcus. So this was the source of quite a lot of the material in this lecture. And second resource, again, this is something that we had mentioned before. And you can see there the different interactive things that you can use to play around with the optimal portfolios. And also it gives you the code to calculate these optimal portfolios in case that is something that is of interest to you for your own work.